Check. That works. Good. We're good. Okay. Hello, everybody. Welcome, welcome, welcome. Come on in. We'll just keep filtering in. We're going to get started because we have a lot to get to today. And very excited to have you all here. Welcome to the inaugural event of the 2023 Land Trust Learning Series. Yeah. All right. So my name is Cindy Elder. I'm with the Barrington Land Conservation Trust. And just take a look around. We're in the beautiful Salem Family Auditorium at Barrington Public Library. This is a pretty amazing spot. And we're very grateful to be here through our partnership with the library. And big shout out to Siobhan Egan, our community engagement librarian, who basically worked magic here to make this all happen. The Barrington Land Conservation Trust is a nonprofit that manages about 300 acres of land. And several of our board members are here tonight. Could you stand up just briefly if you're a board member of the Land Trust? Stand up. I didn't warn you. You know how to do it. Okay. A couple of them are outside. There we go. One's in the back. That's Ian. He's our board chair. And we're operated almost entirely by volunteers. So wave your hand if you have volunteered in any way for the Land Trust, or if you've supported us financially. Just wave your hand. I see a lot of hands. That's great. Lots of hands. Woo! Awesome. So we always need more volunteers, and we always need more financial support. So I hope you picked up a donation slip coming in, and we have another way that you can give back to the trust and actually get something too, because thanks to our wonderful speaker, Mark Bertness, he's brought his book, which came out during the pandemic, A Brief Natural History of Civilization, and for a $25 donation to the Land Trust, you get this book. So on your way out, you can do that, and he can sign that for you. Speaking of support, the learning series wouldn't be possible without support from Chart House Realtors, and our presenting sponsor, Matt Antonio, is here. And just come on up and say hello, Matt.
Thank you. Hello, everybody. It was an interesting thought process that I went through being in the real estate brokerage business when Cindy contacted me and asked for some support. You know, as a real estate broker, we obviously spend a portion of our time thinking about how to develop land and maximize the potential of land. But at the same time, in my head, I thought, gee, I also really enjoy nature hikes, walking the coastline with my family, and all of the amazing things that this area has to offer. And so in thinking about this sponsorship, it really became obvious to me, especially with what's going on in our environment and changes to our environment and everything else, that it's not just important to get out there and enjoy these things, but it's imperative that we support them. So Chart House Realtors is super proud to be involved. We're really thankful that Cindy approached us, and we're excited for this learning series. It seems like it's gonna be awesome.
Great. Thank you, Matt. All right, and a quick shout out to some of our other sponsors, Brickyard Wine and Prickly Ed's Cactus Patch Native Plant Emporium. We are excited to bring Mark Bertness to Barrington for this presentation on salt marsh degradation. It's a concern that's playing out in our own community. Dr. Bertness is the Robert P. Brown Professor of Ecology and Evolutionary Biology Emeritus at Brown University. That's a big title. He's traveled around the world studying shoreline ecology and has authored several books, like this one. So this one's available for purchase this evening. And he wrote one of his books sitting right here in the Barrington Public Library. Maybe he'll tell you about that. Please join me in welcoming Dr. Mark Bertness.
There it is.
There we go.
Thank you so much for that nice introduction. Yeah, it's very true that I did write a book. in this very building. But maybe even more important, I've lived in this community. We've lived in this community in Barrington for all the time my daughter was in school, and we've actually lived in the East Bay for nearly 40 years. So this is really nice to come back to Barrington, where my work with salt marshes really began. Not only did I write this book, my first book, my shoreline ecology book, in the library, because my wife couldn't go on sabbatical with me. I had to find another place to kind of find solace in a sabbatical. But I gave my research program actually started out in the Smith's Cove in 1982 in the backyard of one of the Brown Deans, and also I gave a talk in this very room 30 years ago. So there's just a lot of things that tie me to the East Bay and excuse me, and Barrington in particular. So when I first got here to Rhode Island, I wasn't quite sure what I was going to do. I grew up on the West Coast with nice tide pools and starfish and chitons and limpets in Puget Sound. Then I did my graduate work in Panama, where I worked in both coral reef and rocky shore environments. And then I got a job at Brown, and I found myself in Narragansett Bay, which at least biologically had been scoured out by glaciers and then assaulted by the Industrial Revolution, so that there wasn't a whole lot. Basically, you had weedy species in the cobble, and really the only thing of interest to me anyway was the salt marshes. And at that point in time, 1980, salt marshes really hadn't been explored experimentally. All the work that had been done on salt marshes was correlative work, mentionative kind of work, without kind of an experimental background. And the salt marsh paradigm that had developed was that marshes were controlled from the bottom up, so that you had a physical condition of salinity and temperature, and you get that condition, and that's how a salt marsh would be formed. But this was something that was entirely based on correlation. There had been no experiments done. So I was pretty attracted to working with salt marshes simply because ecology at the time, 1980, was still a fairly young field. It still was a field where a lot of major questions had yet to be resolved. In addition to that, it was a field that experimental ecology, field ecology, didn't really exist until about the mid 70s. And then that just kind of really opened the door to how salt marshes worked, how they're organized, and so I got excited about applying this experimental approach to the New England salt marshes and salt marshes in general, because they are one of the dominant systems on the east coast of North America. They're highly structured. You know, they have nice zonation patterns in them that you know, beg science to ask what was generating these patterns that you see on every marsh you go to that's not heavily disturbed. And also, I recognize that after working in coral reefs and rocky shores, that they were probably a lot easier to manipulate and do experiments with, because all I really needed is a shovel to move plants around and some caging material to keep predators and insects out, and that it would be like almost like working in my garden, and I wouldn't have to be running around with big power tools like I had been doing in the past. So I really got into marshes initially because there was so much that I thought they could offer as a model system for theoretical ecology. I wasn't initially interested at all, and people really weren't worried at all about environmental degradation back in 1980. Now that's certainly changed now, and so through the 80s, we did a lot of experimental work, just trying to understand the organization of these systems, and then around 2000, we did kind of an about face and really started digging in to figure out how humans were impacting marsh systems. And a good example of just how powerful that change was before, from 1980 to 2000, all my graduate students would call themselves experimental community ecologists, and after 2000, they would call themselves experimental conservation biologists. So a big shift there. So today, what I'd like to do is share this experience with you, which kind of started right here in Rhode Island, led me all over the world, actually, and tell you about salt marsh degradation. Some of it, which kind of starts locally and spreads globally, and some start globally and then kind of boils down to and acts locally. So a couple of things about salt marshes that are kind of interesting and interested me initially was salt marshes are actually the most productive ecosystem on the planet by many estimates. You would think that a more charismatic environment like a coral reef or a tropical rainforest would be more productive, but salt marshes actually give agriculture a pretty good run for its money, and are really widely thought to be more productive just in terms of annual productivity. There are also systems that have played a major role in the emergence of human civilization. The agricultural revolution happened on marshes and in this river valley, the Yangtze River in China, and the Fertile Crescent, all kind of based on the productivity of these marshes and the secondary productivity that they produce. So that marshes are really pretty important from both a biological and a cultural point of view. However, you know, we have really abused marshes for a long time. Historically, we have derogatively called them swamps, used them as garbage dumps, continue to use them as garbage dumps in the tropics. And we've ditched, drained, developed, and just really been horrible to marshes over time, and this has resulted in 60% of the marshes that existed in early history having been lost to development. And here on the left hand, I have two diagrams that show marsh loss in the Boston area. And I did this work as a former student of mine, Karen Gadon, who's now a professor at George Washington University in Washington, D.C. But we went through and got historical maps from Harvard, Yale, and Brown, got all old maps together and figured out the marsh cover and as early as we could, and the best records we could get were 1777. And you see the shift from 1777 to 1999 when this data set was complete, and just the total loss of almost total loss of the marshes in Boston over that period of time, and this is a story that's repeated in like Philadelphia, New York City. All the coastal cities have this same kind of footprint, and the remaining marshes that we call undeveloped, they've all got quite a bit of damage to them too. Most of them have been ditched and some of them diked as well. There's only about 5% of marshes on the East Coast that haven't had some kind of human disturbance. So about 20 years ago, ecologists started thinking about what is the cost of all this environmental degradation that we see, not just in salt marshes, but in just natural habitats in general. And it was actually Paul Ehrlich that came up with the term ecosystem services, which just represent how much, basically it's monetizing what an environment is worth. And he suggested this is a concept in the late 80s. And then in around 2000, 2001, one of his colleagues, Gretchen Daly, really went to town on this and started figuring out ecosystem services for all the ecosystems that they could get numbers on. And for example, for a coral reef, it'd be the profits from tourism and maybe protection from waves and also maybe the bio the chemicals that evolve for defenses that medicine can usually mines for are pretty important. So they went through all these different kinds of all these different types of habitats, and it turns out in all of these surveys that were done, and there was really quite a lot of work done for almost a decade on this. Turns out salt marshes are the most valuable ecosystem on the planet in terms of ecosystem services, just from the kinds of services that they provide. I mean, nutrient cycling, water purification, storm and flood control, carbon storage, and nursery grounds. So that really they really check off all the boxes, and so are really quite kind of underrated in terms of but by the general public, at least, in terms of how important they are to us, a really important system. So what I'm going to do today is tell you about how different. I'm not going to talk about all the factors that affect marshes. I'm going to tell you about the 4 that really make a big difference. Talk about nitrogen pollution, invasive species, climate change and sea level rise, and then overfishing and consumer control. I'll skim a little bit over the nitrogen pollution, invasive species, and climate change, because I think you've already had reasonable familiarity with that. We'll talk about that, but I want to focus mostly on the overfishing and consumer control, because that's the most recent problem that you've been having here in Narragansett Bay. Nitrogen pollution, the basic problem is that most natural systems, at least marine systems, were nitrogen limited historically. So the systems were evolved to live very low levels of nitrogen, and made evolutionary adaptations to deal with those conditions. So then in around the turn of the last century, they got a Nobel Prize for this in 1914. Haber and Bosch discovered how to make artificial ammonia fertilizer, and that just kind of changed everything. And so nitrogen fertilizer in these systems kind of turns everything on its head, takes the limiting factor out of the system, and totally changes the rules. And I'll show you how that works in salt marshes. Invasive species are a huge problem. And we think of invasive species as being kind of a now problem. These invasive species really set the stage really during the age of wooden ships and big sailing ships, the ones that were exploring, the ones that had early commerce, because they traveled around and came in and out of ports using hard ballast, so that when to get in and out of their ports, they would weigh down their ship with ballast that was either stones from the intertidal or even more frequently chunks of salt marsh peat that they would cut from the marsh, so that then they would get to the next port and dump that out. So they were literally, just sprinkling these plants everywhere they went. So the invasive species problem really was we still have it, but the stage was really set hundreds of years ago. Climate change, I'm not going to talk much about warming. It's a big deal for us, but when we're talking about marshes and we're talking about Barrington, sea level rise is what we need to be talking about. So, and of course, this is just the overuse of fossil fuel. A lot of coal comes from fossilized marsh beds, leading to solar or thermal expansion of the water and the melting of the ice caps, which is getting to be, even yesterday, seeing the driving down the Wampanoag Trail. If you've lived here for a while and you're not a little alarmed when you see times like yesterday, there's something wrong. So, and then I'll spend most of my time talking about overfishing and consumer control, because for any of you that do walking in the marsh and are, even if you're just driving down the Wampanoag Trail and you look out on the marsh and go, well, wait a minute, didn't that used to be a big green landscape? What's that big black line that's sitting there lining the the shoreline. What's going on there? This is overfishing and consumer control. And so I'll spend a lot of time talking about that. So eutrophication. Eutrophication is this overuse of artificial nitrogen fertilizer for the most part, and this was thought to be kind of the miracle of the modern age. In 1914, this is Thomas Malthus had said, God, the world's going to run out of resources by about 1890, and then Haber and Marsh invented artificial fertilizer, and it ended up pushing the population up so high that then we're all dependent on it now, that it's really driven the environmental crisis. Whereas when it was invented, it was thought to be the greatest thing since sliced bread. So nitrogen fertilizer, increased temperature, you mix those together, you get algal blooms, anoxic substrate, and dead zones. And by dead zones, I mean areas on the bottom that have no oxygen at all. That there's been enough productivity that the microbes have eaten up all the oxygen, and you have a total dead zone. Now, and the signatures of this in Rhode Island, I'll get to each one of them, are algal blooms, fish kills, sludge, cohogs, and phragmites. So the first sign, actually, that there was a problem in Rhode Island happened in the early 90s, 93, 94. There were some fish kills, so that dead bait fish, menhaden, were found stranded in this beach strand line down in East Greenwich, and this made the front page of the Projo back when there was a Projo, and when everybody read the Projo, it made each time it happened, it made the newspaper, and they would talk to the people at DM, and they really would just kind of shrug and say, "Let's pollution," and that was basically saying we don't know, because they didn't really know what was going on. Then a very large fish kill happened. Same thing. Fish washing up onto the beach near Goddard Park was one of the big spots that this happened. But this time they knew what happened, because in Louisiana the previous year there'd been a big find where a group of ecologists at LSU discovered that there was a huge area off the coast of Louisiana in the Gulf of Mexico, the size of Texas, that was totally anoxic, and that was everything was totally dead. You know, the things that could swim out of there got out of there, but it was, killing everything else, and that this was the result of overuse of fertilizer in the Mississippi River and the tiling of the Mississippi River to maximize use for agriculture, and particularly over fertilizing, not dosing it properly, just saying, well, hey, if a little, kind of make America better kind of thing. It's like, let's put more fertilizer on there. And so they did. And And they ended up creating this huge dead zone that is not even, it's not even a seasonal feature. It's their a permanent feature of the Gulf of Mexico. And nothing can actually live in this Texas-sized area. Eutrophication, probably last week we heard about this big blob of seaweed that's washing across the Atlantic. This is probably largely due to eutrophication too. There are other things that can feed into it, but my bet is that a large part of it is general eutrophication. But once they discovered this, we discovered that just about everywhere you look, where there's a big river and a lot of industry, you have these dead zones happening. And then in Narragansett Bay, you started seeing these algal blooms. Just a little bit, they're getting to be more and more common. These are the things that you read about in Florida on the Florida Panhandle, where people don't want to go to the beach in the summer because it stinks so much. This is eutrophication manifesting itself in terms of algal blooms, which are becoming more and more common here. Now, why do we have quahogs here? Well, so once this became clear, the scientists at a coalition of scientists from Brown and URI started looking at the bottom in seasonally, and realized that there would be seasonal dead zones that would happen in the end of the summer every year. And this would basically drive out all the mobile organisms, but the things that couldn't move, would die. The only thing that survived this was the quahog. And the reason that the quahog survived this was that evolutionarily, quahogs always had a problem with predators. Their predators were olfactory predators, mostly thinking about crabs and stuff like that. And they would get around the predators when the predators were around by holding their breath. They would hold their breath. And what the problem with holding your breath, it's the same thing as with running too much, is you generate an acid, anaerobic metabolism has an acid byproduct. So quahogs were doing the same things that turtles do, turtles that hibernate over winter underwater. They were using an anaerobic metabolism and then using the calcium carbonate in their shell to buffer the system. So because of this pre-adaptation, quahogs became our state clam. And Ian McFarlane totally took advantage of this. And if you are in Europe and you say you're from Rhode Island, people think you're from Long Island. But if you say you're from quahog, they know exactly where you live. I don't know where my wife is, but this happens all the time to us when we're in Europe. So another huge thing that's happened with eutrophication is it's triggered this massive movement that we've seen since starting in the late 80s of Phragmites into the marshes. And we've spent a lot of time working on that. I'll show you how that works, but I gotta tell you that it's not a real simple problem. One of the Phragmites has been here forever. The Wampanoags, the Poconokeets, they made their huts out of Phragmites. It's been around a long time. But there was, in the 70s, there was a genotype of Phragmites introduced here from China or from Asia, I think. I don't know if they know the exact location, but it's an Asian strain of Phragmites, and it's the hybrid of between the native species and this Asian Phragmites that's been spreading around. So that's kind of the under the backstory here of how Phragmites moves around. But let me tell you how it ended up. I mean, we were so confused when we first started seeing this happen. Been working around marshes, all of a sudden Phragmites is acting like it's like a massive invasive species, and we knew it wasn't. But then we started working with the Phragmites invasion. In order to do that, to explain this to you, I'm going to have to explain to you how the plants are zoned in salt marsh. I mean, you know, when you look out on a marsh landscape, you see all the octogenarians, you know, there with their paints, painting the nice zonation of the marsh. It's so easy to draw. So if you go out to any marsh around here, any marsh, unless it's been massively disturbed, what you'll see is the low marsh, which is simply that part of the marsh that's flooded on a daily basis, no matter what. That's dominated by spartina alterniflora or smooth cordgrass. And this boundary between the low and the high marsh used to be something like an atomic clock. You could, you know, set your watch by it. But then above that, you have a zone of marsh hay, which is in colonial times, that was the grass that the farmers encouraged would drain things so that they could enhance the production of marsh hay, mostly for fodder. And then above that, you have Juncus gerardi. That's the green plant, the green perennial that you see coming up in the marsh really early before anything else is out there. That green line that will form up right below the woody vegetation. And then running around in patches, you'll see Distichus spicata, another plant that's more of an opportunist colonial thing that runs around and takes advantage of disturbances to live in, find a place to live on the marsh. So when we started working on these marshes, the going hypothesis, or what you would read in textbooks, was that each of these plants, Spartina alterniflora here, patens here, Juncus here, Distichus there, was growing in the habitat that they were adapted to live in. Kind of like a big smiley face, kind of explanation of how these things, how these communities were organized. But they'd never tested this. There's been no tests whatsoever of that hypothesis. So in the very early 80s, one of the first things we did is we said, is this basic rule of zonation in marshes, is this valid? Very easy thing. We went and got shovels. And then we did clonal transplants. That's technical term for shovelful. And we took shovelfuls of each one of these species, alterniflora, patens, Distichus, and Juncus, and we moved them into bare spaces at all tidal levels, so that they didn't have direct competitors. And every single one of them grew best right up here at the top of the marsh. Every single one of these plants would rather grow in your backyard than actually grow in the marsh, because these are stressful habitats. These are vascular plants. They don't like salt water. They don't like anoxic soil conditions. As you move down into the marsh, the salt water and the anoxia that develops down there is very toxic to plants. They can't pick up nitrogen, even if it's there, if there's no oxygen in the soil. So right off the bat, we realized that the old paradigm, that the correlative paradigm was wrong. So the next thing we asked was, well, what's driving the zonation? We know that they all can live everywhere and grow best up on top. What's driving the actual zonation? These are habitats that unless they're disturbed, they're entirely saturated with plants. You know, just like a nice lawn. So there's very little bare space except when you get disturbances. So we figured that, you know, it might be plant competition. You know, plant competition might be important. So what we did is we went across this gradient and did those clonal transplants again, except this time and I'll just take the alterniflora patens border for an example. We did reciprocal transplants with and without neighbors at all the borders: alterniflora patens, juncus, disticulus, juncus, disticulus, or patens, disticulus, all combinations. And every time we did it, we'll just stick to the alterniflora patens border. When we took patens and we moved it down to the lower zone with and without vegetation, it died either way. And so physical factors were limiting it from moving it down. If we took alterniflora and we moved it into its own habitat, fine. If we moved it up a zone and we left the neighbors intact, it was competitively excluded within about a year. But if we kept it clear of neighbors, it did better here than it did down in its own habitat. So what was setting up this competitive hierarchy here was Juncus gerardi was competitively excluding Spartina patens and disticulus to living in the lower part of the high marsh. And all these high marsh plants were limiting alterniflora to live in the low marsh place, the worst place for it to actually grow. The next question we had was, well, what are they competing for? We knew that nitrogen was a problem in marshes. So we did fertilization experiments at each one of these borders, at the alterniflora patens border, at the patens juncus border, and all the borders with disticulus as well. And when we added nutrients, and this was such a dramatic result that the Brown undergrad that I had monitoring this with me, he like quit. He was like, things changed so fast that he thought he was screwing up, you know, and he like ran from the experiment. We had to get a new crew working on it because the first guy this was too big a result for him to handle. And because when we done fertilizer, alterniflora became the dominant species on the marsh. It beat out patens. Patens beat out juncus. Juncus became the low plant on the totem pole. So this total reversal of the competitive hierarchy. So that in the native environment without nutrients, alterniflora lives down here, is a competitive refuge. Patents lives here as a competitive refuge from juncus, and Disticus lives in bare patches, running around for its life in bare patches, and gets squeezed out within a year or two. Well, what about Phragmites? And also, why does this? Why did this happen? Why did we get such a dramatic 180-degree change in the competitive hierarchy? Well, we took nitrogen, which was the most limiting factor in these marshes, and we made it not limiting at all. And so what was limiting these plants and determining competitive battles was not nutrients, but light. So that since there was a nice trade-off between density of root mat and above ground vegetation, the tall plants became the dominant plants, rather than the plants that had the most dense nutrient grabbing root systems. So and so here's basically what happens for Phragmites to dominate a marsh. You get shoreline development that's taking away sorry for the realtors in the crowd, but taking away the woody vegetation surrounding the marsh. That takes away the buffering and the processing of the nutrients running down into the marsh. This increases nitrogen input into the marsh, and the plants respond by alterniflora starts motoring up higher marsh elevations. The Phragmites, which initially used to live in the high marsh because it had mycorrhizae, it had nitrogen fixing fungus that were mutualists that were helping it live in that environment. Added nitrogen to it and said whoopee, and just started moving down to the low marsh, and at really high nutrient levels, Phragmites actually takes over and it gets a much higher stature, so can actually limit Spartina alterniflora to a fairly small part of the low marsh. And here, just to show you, ecologists rarely get physicist kind of results. But this is within Narragansett Bay, about 25, 30, I can't remember which, marshes. We looked at the percent of the border developed. By developed means simply removing the woody buffer, and Phragmites, the percent of Phragmites on the border. This is a 95%. Takes 95% of that variation of Phragmites is due to the border or not. And this result ends up being the Nature Conservancy thought this was the best thing since sliced bread, because all of a sudden, when somebody came into the DEM office or came into to talk to the land trust and say, I have Phragmites coming into my backyard. What are you going to do about this? You could pull this out and say, are you fertilizing your lawn? Are you taking away vegetation on the border? And they would say, yes, we're watering our lawn, we're fertilizing our lawn. They're saying, you're farming Phragmites. So here's where we kind of cross the bridge into working on much more applied kinds of things, when we ran into a result that every conservation group on the East Coast wanted to know. One other thing, just to get you kind of comfortable with Phragmites, when you see these big stands of Phragmites, don't think of them as individual plants. They are literally big clones of organisms kind of crawling like an amoeba across the substrate. They're they're all clonally integrated. I mean, if you bug a plant out here, somebody from in there is going to send it nutrients and fight back. And it allows Phragmites, this clonal advantage allows Phragmites to move into really nasty habitats that he could never get into sexually. You know, there's no way it could live in some of these muddy habitats. But clonally, it's not a problem. Just goes right through it. So when you're driving down Wampanoag Trail and you see those big patches of Phragmites, those are clones, not just individual plants. So do you understand Phragmites now? So I wanted to say a bit about anthropogenic sea level rise as well. If you follow, this is as new a figure as I could get, and it's not up to date. Things are changing so much. We've realized every time that new predictions are made, they're exceeded within 6 months. So the newest predictions have used artificial intelligence and machine learning, and the new predictions are that within the next 10 years, we're going to have a 1 foot increase in sea level rise around here, and by the end of the century, we're going to have 6 to 12 feet of sea level rise. Barrington mean sea level is 6.5 feet. So and we actually, because we were working with zonation, we saw this coming in 2000. We were doing some marking some quadrats to follow over time, and in the 80s, and put some quadrats down on the high marsh, low marsh border. And one of my students went out to find these things for some work we were going to do, because after a number of years, these things are hard to find, and they came back and said they're not there. So I had to go out and show them where they were. I got there and I didn't think they were there either. But then I realized that no, they're there. They were just sitting up here now, because sea level had risen enough so that it had driven the low marsh higher already, and I got a geologist, geology graduate student involved on the project, and it matched the tidal elevation information that we had at hand. So what are we looking at in terms of what's going to happen to the East Bay? This is a diagram put together by Senator Whitehouse's office that used the sea level rise predictions and the topographic maps, and layered them over. Basically, the East Bay is going to become an archipelago. It's going to become a string of islands. There's going to be Princess Hill Island. There's going to be Rumstick Island. There's going to be Bristol Highland Island. And then there's going to be, where I live, Wisset Island. But this is what's going to happen. And how do you sniff this out? When is this starting to get dangerous? And we really have to worry about it. Well, this is a ghost forest. One of my students, I've already mentioned, Karen Guidon, has become one of the world's authority on ghost forests. And she's studied them all over the world now. But my wife and I were just driving up from Savannah a couple months ago, and I was just dumbfounded at how common they are now. Because as you come up the highway from Savannah or from Florida, you're really skirting marshes. So you're really getting a nice look at marshes. And this is a very common sight of the edges of the highland woodlands, just totally dead and standing. What happens is the salt water gets up there. You get saltwater intrusion into the root zone, and then you get the standing plants, dead plants. Hummock areas, if you know what a hummock area is on the southern marshes, there used to be these beautiful little spots, high spots on the marsh that had nice green vegetation. Maybe if you're lucky, a live oak. They're all dead. They're all just standing dead. So and as you come up, now we've already destroyed most of our large marshes here, most of our low-lying marshes that were easy access marshes. So we don't have that many marshes where we're going to see this really early. But I would guess within 5 years, we're going to start seeing in 100 Acre Cove. We saw that Phragmites come in. This is what that's going to look like. You're going to see at the top of the 100 Acre Cove. You're going to see the dead trees, and that's when you put the for sale sign, because that means things are really starting to motor up. So now let's talk about the really dangerous stuff. The really nasty stuff that's been going on here in Narragansett Bay pretty intensively for the last 10 years or so. And something that we discovered out on Cape Cod, right under the nose of Marine Biological Laboratory at Woods Hole. But so old ecological theory predicted that, and or hypothesized that bottom-up forces of nutrients, temperature, were what drove the production and structure on marshes and other systems. The salt marsh model that was developed in the 50s and 60s, early 60s on Sapelo Island at the University of Georgia, that was exported to mangroves, to tropical forests, all over. Basically is a fundamental rule of ecosystem ecology. But in 1960, a hotshot group of kind of cocky Ivy League guys went to the University of, were graduate students at University of Michigan, and they came out with the green earth hypothesis. They said, no. Nutrients, they may be pretty important, but predators are probably more important, because predators keep herbivores in check. If you take the predators away, the herbivores eat the plants. It's called a trophic cascade. Once that was Harrison Smith and Slovakian wrote this paper, one of the most cited papers in all of ecology. But it was initially shown in some rocky intertidal habitats where Pysas, or a starfish, was having top-down effects and control on an island off the coast of Washington State. That was the first really bona fide example of this. That's the whole keystone species concept came out of Bob Payne's work on this. But the real charismatic example that caught everybody's attention, I mean, a lot of people, think starfish are jewelry and are not that familiar where starfish live and what they actually do. But Jim Estes was also at that time at the University of Washington. Did his graduate work with a guy named John Palmisano and with Bob as well, and showed that the disappearance of the kelp beds that was happening on the West Coast was due to removing sea otters at the turn of the early 1900s. Sea otter hats became kind of the rage, like popular. They getting a lot of hits, kind of thing, and so sea otters were eating all. We're out of the picture. The urchins started multiplying like crazy. Urchins, they have this thing called an Aristotle's lantern, which is how they scrape the surface for their food, and it's basically 5 razor blades kind of scraping together, and they can eat anything on a surface other than a calcified algae. So this is what kelp beds started looking like with the absence of otters. This is called an urchin barren, and fortunately, Estes got into this early enough so that through the 90s and I guess it didn't really happen until the early 2000s, they transplanted sea otters back into the coast of California, and the kelp beds came back. Not always possible. It's great. It worked for sea bass, too. But this was the first really great example of it. Same things happened at Yellowstone Park. They got rid of the wolves. All the vegetation went down. They realized, oh my God, ranchers aren't going to like this, but we got to get the wolves back. And then the vegetation came back. It's happening right now in African savannas. There's this big push because it's being devegetated so quickly to rewild Africa, to get predators back into the environment so that they'll take care of the herbivores and will bring back the vegetation. Now, this wasn't supposed to ever happen in a salt marsh. There were down at University of Georgia, Sapelo Island Marine Science Laboratory, there were people that sat around with jars with this snail in a jar, and they fed it fungus, and this was their proof that this really abundant snail could live and survive on fungus alone. Pretty lousy experiment, but in the early to mid 60s, a guy named Bob Jeffries, good friend of mine who died not too long ago, moved. Crazy thing. He moved from Cambridge, England, to be a professor at the University of Toronto. Back when the University of Toronto was mad as hell that they weren't thought of as the best university in Canada, and they wanted to, steal the thunder from McGill. So they were like the University of Texas. They were buying a university, bringing in good people. Why would Bob leave such a nice place for Toronto? I like Toronto, but it's pretty cold there. Well, Bob's specialty was halophytic plants. What's a halophytic plant? A halophytic plant is a salt-loving plant. These are plants. There are very few of them, but that a lot of them plants have adapted so they can live with salt. Some have evolved so much that they can't live without salt. So where is the hot spot of halophytes in the whole world? The Siberia and the boreal areas around in Canada. So he was excited to be able to come over to the University of Toronto and work with the halophytic plants up around Hudson's Bay. And here's what they look like. And here's what they looked like in 1965. And if you look at this landscape, this is a totally vegetated landscape, but it's on a the soil hasn't developed yet. It really, this looks like the glaciers receded yesterday or a month or two ago, because there's very little rooting here. The sediment is just maybe 10, 15 centimeters max, not very good sediment. These rocks you see are glacial erratics. You know what a great glacial erratic is? When you're hiking around in New England, you see those big rocks out in the middle of nowhere, and you go, how in the hell did that rock get there? It got there because a glacier melted back and just left it deposited there. These glacial erratics are so small, you could collect them and put them in a bucket. You know, so this is what Bob found initially. He did some initial experiments which got a lot of attention. He put some removal cages out to prevent the geese from feeding in these plots. And what he found was that if you remove the geese, the plants didn't do as well. Turns out that now living in Barrington, you know how geese feed. They don't feed on the green stuff; they feed on the roots. So these guys are feeding on the roots, and they're pecking around at the roots, and they're turning over the substrate, and then they're recycling the nitrogen. So at the low densities that the geese were at this time, they had a positive impact, positive feedback with these plants. But then what happened, you know, we were overusing nitrogen fertilizer across the United States and Canada. Here's a couple just dramatic demonstrations of just how dramatic that was. Here's nitrogen and phosphorus fertilizer in metric tons from 1960 to 2000 with the nitrogen curve. And then here's the area of different pasture land. So we're increasing the amount that's being put down and the area that's being put down. And as a result of that, the geese population are going crazy. You know, they're just increasing dramatically. So from the time Bob went there initially in the mid 60s, and they're here, and then by 85, where I'll show you the next picture, they're here. So what happened to this habitat with the geese grubbing was that's the very same spot looking at, across the landscape. More of the glacial erratics are actually exposed. And here's a picture of an area that Bob, who was a pretty primitive cage builder, I must say, had managed to keep the geese out. I mean, geese are pretty easy to keep out because geese don't duck. You know, if you put a line around it or just something like that, they will not go over it, and they won't fly into something that small. But this was very dangerous work because there were polar bears up there. So Bob, whenever he worked up there, he had to have spotters around because, you know, bears, we're natural prey for polar bears. So they would crawl. Polar bears would get down and crawl until they're about 100 meters from you, and then they would break into like a 30-mile-an-hour run. And if you didn't get it with the tranquilizer gun, you were gone. I mean, these things would go through cinder block walls. So it was pretty dangerous stuff, but this was a pretty dramatic result. Bob, this made the cover of Science section of the New York Times, along with a cooking piece on how to cook duck. And And so, but marsh ecologists in general basically said, that's just, that's in Canada. That's not in my backyard. That would never happen where I live. It's just, yeah, something like that. There's just, but anything. But it wasn't. They were huge results that were almost ignored, even though they were cover of Science, cover of New York Times kind of things. So then about 7 years later, there started being die-offs in southern marshes. These are these massive marshes that you have down south because of they weren't eroded, they weren't washed away by eroded away by the glaciers or the erosion of the Appalachians and all the shores. And this is Keenan Marsh on Sapelo Island, Georgia, where the University of Georgia Marine Lab is. That's about a 250 hectare marsh. It's a good sized marsh, but that's not unusual for a marsh there. So they started seeing die-offs in the late 90s, and they were, oh, this has to be a drought, or this has to be anything, a flying saucer landing there. I mean, they were groping around for reasons that this could possibly be happening. But then if you look at these, if you look carefully here, what you see is, there's really tall green stuff here on all the borders of the marshes. Then as you go into the interior, it's a little darker. And if you zoom in on those areas, what you see is they're just studded with snails, little snails called littoraria. They're very similar to the littorina you find here. You could fool an amateur easily with them, but because this is a barrier island, because the Gulf Stream comes right by it, these snails, which have a larval delivery, larval life form, were being delivered to this island at such extreme densities that the density of snails randomly on these islands, on Sapelo Island and the other Cumberland and Jekyll and all, were 500 to 1,000 snails per meter square. A lot of snails. So we thought, ooh, this is something that we should probably look into. So we went down there and realized, well, you have 500 to 1,000 snails randomly. What can I find in 5 minutes? And what you could find in 5 minutes was 4,000 plus snails per meter square moving around in a feeding front at the edge of these bare plot patches. And we looked it up in all the old texts from the marsh ecologists down there, and these snails were like supposedly just munching on fungi. Like they were sweeping the kind of the boxes of the model clean, kind of taking cleaning up so they assumed that this was not, grazing was not involved, and that there was no active consumption here. But that assumption was never tested until we went down there and did it. So with my student Brian Silliman, who had done some work with this already in Virginia, based on some of the work that I had done out at Haffenraffer with the big Spartina patches that you have there. We put out large enclosures raised at 2 different marshes where we manipulated abundance, and both in the high marsh and the low marsh. The low marsh doesn't really normally have snails because they're picked off by blue crabs and turtles. but the high marshes where you have these really massive densities. So we had 1,000 snails, 500 snails, and no snails replicated 8 times in these galvanized cages. And the galvanized cages, that's done on purpose. The snails kind of lead with their tongue, so they lick where they're going rather than look where they're going. So galvanized hardware is covered with zinc, and it's just like copper. They just lick it and turn around. So once we set these things up, they stayed we didn't have to do a whole lot of maintenance on them. We could go back to Rhode Island and have a little fun, and then go back to Georgia and with these cages. So what happened? So here's what happened where we basically remove snails from the high marsh. And anytime you can get a photogenic result with plants, this is strong evidence. But we removed snails from the high marsh, the stunted high marsh, and we increased productivity by 1 order of magnitude in 1 summer. This is before the feedbacks of shading and habitat amelioration kicked in. This result grew over time, but you know, once we got this result, we had to watch our backs actually. So this is what happens in the low marsh. Now let me show you what you're looking at. This is 2 meter tall cord grass. This is what you find down in the low marsh on Sapo Island. With 1,000 snails per meter in 1 season, 2 months, they have eaten everything from including everything below ground. Everything's dead as a doorknob. 500 snails, it takes 2 years for that same result to happen. So just total consumer control of the low marsh. So, and here's another interesting. We did the same experiment in Louisiana just to have fun and to go to Louisiana. And so we put this cage was initially on this edge here, and we came back, you know, after a couple months, and the cage is out in the middle of the bear patch. It was being eaten away. And here's your trophic cascades. Blue crabs, which were being over-harvested to the point where disease was getting them. Turtles, which are ecologically now extinct, they're there, but ecologically they're not really there. And then there's some other smaller crabs too. But you remove most of this, and the snail goes crazy and takes off after Spartina, and it's not totally eating it. But it's actually, these plants end up, it eats a little bit of it, like maybe 10 or 15% of what it's doing is eating the plant. But what it's mostly doing is with its radula, its tongue, which is a scraper, it's scraping the scars onto the plant, and ultimately these scars get infected, and the plants are dying from the infection of the plant. So it's actually a disease story. And Brian has done some really cool work where he's the Rachel Carson Professor of Marine Biology at Duke University now. He did some work at low densities. What these snails are doing is farming the fungi. They're eating a little bit of fungi, pooping on the plant, and increasing the fungi. So they're actually farming it at low densities. Well, Brian and I went to a talk, and we went to a big meeting, and we gave back-to-back talks. And my God, did we cause a rumble? I mean, this was just shook the bedrock of a whole group people who had bet their careers on these being bottom-up systems and the Odom doctrine, that plants were not eaten in salt marshes. This doctrine that had been imported or exported to all these other systems. So people were so agitated about this. We had trouble publishing these papers. This paper ended up not in Science, but in Proceedings of the National Academy of Science. And I mean, ultimately, we had papers there too, but we had a lot of pushback. So as any, in any, those of you old enough to have actually watched boxing on television know that when you have a knockdown, you're supposed to go to a neutral corner. So what we did is we set up some experiments on saplo that didn't need any maintenance for a while. And then we decided to go to a neutral corner. So we decided that Patagonia would be a nice place to go. So we went down to Argentina, where Alfred Wallace had described the marshes. And we knew that there was a crab down there, but nobody had worked in these systems. Nobody really went to these systems. So the Mellon Foundation is real happy if we would go down there and train some students. So we got some money, went down to train students. And here's what we saw when we got there. Unbelievable. This is a high marsh, and the plants are totally restricted to this area in the high marsh. And there are so many of these crabs. And this is Chassid manus, is a crab. I said a big one is like that, maybe a little bit like that across the carapace. But these things are at ridiculous densities. I mean, it's like an ant farm. There are hundreds and hundreds of them per square meter. They're just incredibly common, but you don't find them up above here. So of course, what do? We did an experiment. How do we do it? We basically just took a clonal replicate shovelful of these plants up here and brought them down to this lower area, and either left them in a cage or not in a cage. And here's what happened. If we left them if we caged them, they started actually growing better than they were growing in their normal habitat. If we didn't cage them, within a week, they were gone. So this was just another example of total consumer control by yet a different type of consumer. So, but this was kind of frustrating because we lived in New England, and there wasn't, what was going on in New England. And then about the time that we were working in Argentina, and that we were getting that work done, there started to be kind of reports in New England and in Rhode Island and Massachusetts of areas of die-off in these marshes. But I was kind of skeptical because we had been to that marsh that day or the day before, and they were finding areas that the areas in marshes that get covered by rack every year and die because it's covered by the dead plant material from previous year. They were calling those die-off areas, and so we kind of went back and forth. But there was this one guy. So I thought it was like an internet problem, too much communication, not enough information, kind of thing. So, but there's this one guy that was the biologist at the Cape Cod National Seashore, and he said, you got to come out and see this. This is going gangbusters out here. And I said, well, go out and look. These are nocturnal crabs. I call them the nocturnal hippie crab. They live in big communal burrows with little side pockets in them. And when I worked in Smith Cove, there was one little area about half the size of this desk that had this crab in it, this Sisarma crab in it, but they were pinned down in that area. They didn't go anywhere. I said, there is a crab out there, but it's nocturnal. And it's like, he was a government employee. He couldn't really go out at night. It was against the rules to go out at night. And he had students, he couldn't take the students. So, you know, and I said, so I was thinking, what a weenie, you know, I get out there. And so a month goes by, and then just, I don't know, he wasn't trying to bust my ass. He was really just being, you know, he was being too much of a rule follower. But he, 8 o'clock, one Monday morning, in August, end of the season, I get this frantic call from Steve Smith, this biologist. He said, we went out there, they're all over the place. And so I went out there with one of my undergrads, Christine Angelini, who's now a really hotsy-totsy at the University of Florida, runs an ecosystem engineering group, but she was just an undergrad. I'd stolen her from the ice hockey team. She'd been on the pre-Olympic team and decided she liked biology better. Actually, it was really, she didn't like the fact that everybody on the ice hockey team looked down on her for being a good student. But we got along real well, and so she jumped ship, and she was with me when we went out to look at and see what Steve was talking about. And this is what he was talking about. We went out to this marsh, and now all this Swiss cheese, this is all old burrows, all old burrows. The action is happening right here. All the live crabs are up here living in these burrows. There might be some down here doing other things, but this eroding cliff here is what's happening to the entire marsh. If you look here, this is, I think, out of Dennis. But as you can see, as far as I can see, you know, there must be, you know, 10,000 crabs, you know, in this strip, because there are hundreds of them per meter square, and they prefer the below ground material to the above ground material. So they're mostly spending most of their time below ground, and you don't see them during the day. They're nocturnal, you know. So and here's what their burrows look like. You know, it looks like somebody just eating corn on the cob on the surface. And here's what these guys look like. They're not hard to see. You know, they're pretty neat, nice, pretty neat crabs. And so here's just a comparison. Here's Narragansett Bay at that time, with a big. Some of you that lived here a long time, you remember these marshes that have the 2 meter tall Spartina alterniflora. This is what it was like when these die-offs started happening in Cape Cod. This is now what it looks like in throughout much of Narragansett Bay. So what do? Did an experiment. But you know, Steve called us so late in the season. Well, how are we going to do this? You know, we can't really put cages out. You know, the damage is it's already been done. You know, so we decided to make little kind of popsicles out of hardware cloth. We took cores of live plant material and we brought them down to the die-off area, and we either had them wrapped in hardware cloth or not. And within a week or so, the ones that weren't covered were eaten, and the ones that were inside were just fine. So we were definitely in business. We looked across Cape Cod at different marshes, and there was real strong correlation between the Sisarma and the extent of the die-off and grazing. Then we did historical work on looking at old maps. And we realized that this just didn't start, you know, last year. This had been going on since the late 70s, since like 1978. These things have been growing and growing and growing right out at Woods Hole. We had just now kind of ran into them. To find out whether these were predators, the predators were responsible for this variation in crab density. We collected crabs and we tied them in little harnesses, like you see some women at the mall with the kids on the end of the harness. But we would sit with students out there for hours. We would string up, put a little dab of super glue on the back, so it'd be fine. And then we would go out and we would put them out just for overnight. When we did that at marshes where there wasn't a die-off happening, 90% of them were gone in the morning, and you'd see the fragments of the shell still stuck to the super glue. And where the die-offs were happening, these things, the crabs basically just set up shop and started talking to each other, and they were fine. They were just happy, and we left them out there actually, and some of them lasted the whole summer just out in the open. So what's going on? Well, we had some data on this from government stuff, both tautogs and blue crabs were coming down in numbers. So here's our working hypothesis. There's Homer up there, and with all the infrastructure that's been been built since World War II, out on Cape Cod. Cape Cod before World War II was just a sandbar with some nudist camps and paint camps and summer camps, but there wasn't much. There certainly wasn't many people that many people living out there. But after World War II, there's all this infrastructure for there's like 500,000 people that go out there just to fish in the summer. So they're knocking off the fish. Fish don't knock off the crabs, and the crabs are living in these nice, comfy communal burrows and eating the leading edge. So to test this hypothesis, we found 14 marshes, 7 that were dying off, 7 that were that showed no sign of die-off. We made these marshes as close together as possible, paired them as much as we could, and then we'd look for this kind of comparison. And the results that we got were very striking. So here's the angling intensity. We did surveys where we looked at sites for a number of set hours a day for fishermen. I found none of them standing in their mud at the undeveloped marshes, but plenty of them standing on docks and boats in the developed areas. The predator biomass was twice at the undeveloped marshes than it was at the developed marshes, and so forth and so on. The predators were being removed. The crab densities were going up, and at the developed marshes, the vegetation was being killed. So, and then one real interesting thing is to look at this historically. If you look at it historically, this is undeveloped marshes over time, and I think this was a set of about, I think, about 20 undeveloped marshes, and then these are a similar set of 20 marshes that were experiencing die-off. And you see at the die-off marshes, there's a strong black line here, and that's the loss due to development. You see the stop there because of the the Wetland Protection Act kicked in 1976, I think it was. That, yeah, so that happened then, and then after that, you see the increase in die-off occurring entirely due to cisarma. Well, let me just tell you one other really scary thing, and that is that these things aren't happening individually. You know, like you're not getting there. You know, one marsh is getting invasive species, another marsh is getting sea level rise, and another. It just doesn't happen that way. Multiple stressors interact. They don't interact, and they don't interact in an additive way. They interact in a synergistic multiplying way. And we've now done this all the way down to Florida. This is a big group of Brown students and I did this. Christine, the hockey players there at the end. This is Saquatucket Marsh, and it's because of sea level rise. It's what's happening is the substrate. This line stays there because of substrate hardness. When it gets saturated, it gets soft. When it gets soft, it gets burned. That's happening on Cape Cod. That's happening in the south, in Georgia as well. And then one last example, just because it's so interesting, and that is that the same kind of thing, interactions happening in China. These are the iconic red marshes of China, and they're really important culturally because kind of like the Las Vegas of China. Everybody wants to go there and get married and have their wedding pictures taken there. But I mean, so they're it's very important to them. And also, this is a major stop on the Eurasian or Austral Asian bird flyway. So this is a mandatory stop for birds. Well, so shorebirds. So what's happened here is that when these marshes started getting eaten up by invasive Spartina alterniflora that had been introduced there, the Chinese government got so crazy about this. They spent a lot of money to go out and kill off the Spartina alterniflora manually and chemically. And then they sent the biologists in to restore these marshes, and they couldn't do it. Why couldn't they do it? The flyways are getting so low that crabs were dominating the landscape, and everything was eaten by crabs. And this is something I'm working on with one of my students now. So my wife told me I had to end on a positive note. So I think the only positive note is that we need some cooperation here. You know, if we don't have any, we can't cooperate in this country, let alone across borders. But the good news is that so Homo sapiens are handyman. That's what Homo sapiens means. But Homo erectus was also pretty handy, and so are Neanderthals. What really distinguishes humans is our ability to cooperate. I mean, it's not just within a family unit, it's among family members. We built up the International Space Station, for Christ's sake. And the agricultural revolution, that was all about cooperation. We didn't go up there and start domesticating plants. It was an evolutionary process that started the domestication of plants and cooperation that resulted in civilization. Same thing with the Industrial Revolution, and now we're watching the same thing play out in the information age with the digital revolution. And we're seeing rocky ride, but our history is that cooperation will win the day. So that's all I have to say.
Dr. Bertness, I think what we're going to do is we're going to take questions outside, because since I know that Siobhan has to close up this room, but we have some goodies out there, and we'll just chat and get our questions out there. Okay, thank you.
Here.